I've written it down here so you can see it again. Want to look at two final consequences. These are very important and interesting consequences that flow from Snell's law for refraction. You see here that there's a sine theta on both sides of the equation, sine theta 1, sine theta 2. And you know sine theta, the biggest it can ever be is plus 1. 0 plus 1. And you might be worrying, gosh, would there be any circumstances under which it would be hard to satisfy Snell's refraction law, Snell's equation? For example, suppose that I had already a fairly big sine theta 1. That's corresponding to a large angle away from the normal, kind of hitting the boundary. There's a boundary between a, sorry about the color coding here, this is supposed to be a low index of refraction medium, a high index of refraction medium, and here's a low index of refraction medium. So the color coding is similar to what we've seen before. This could be water, it could be glass. And so when you're going at a high grazing angle towards this surface where the refraction is going to occur, this number could be very large. And then if you add on top of that the possibility that n1 is also very large, you might easily get into a situation where the left hand of this equation could get to be larger than 1. Would that make a problem for you to solve this equation? Let's suppose that this left side was getting larger than 1. Then suppose that the boundary goes to air, for example, or a vacuum, where n2 is just 1. Could we solve that equation? We'd have something that's bigger than 1 over here, equals 1 times sine theta? I don't think so. That is going to not have a solution. Well, Snell's law is telling you something in that case. If you can't solve this equation, the light rays cannot solve it either. They cannot refract out of that medium, contrary to what we've been looking at in previous cases. So this is shown by the diagram here. If you go fairly close to the normal, you go, for example, passing from water or glass out into air, you'll bend away from the normal. This angle theta 2 will be larger than theta 1. Oh, by the way, just for fun here, we're also showing the reflected wave that comes back at a reflection angle, which is the same number of degrees away from the normal as the incident angle. But that's for reflections. For the refraction, the angle has gotten bigger here because we're breaking out into a low index medium. Now, hit at more of a glancing angle. Reflection goes down like that. At a glancing angle, the refracted wave is really going almost sideways here. So this angle is now getting to be a large piece of 90 degrees. What's going to happen when theta 2 gets up to 90 degrees? That's shown exactly here with this ray. We come in at a big glancing angle where an angle theta c, theta critical, we'll see why it's called critical in a second here, we're a critical angle away from the normal, a glancing angle, and at that critical angle, the refracted ray is 90 degrees away from the normal. See, that's a right angle there. In other words, the refracted ray, if there is one, you're not going to see it because it's refracted just along the boundary. In other words, it isn't really getting out. So if you're just like 1 degree above theta critical, no refracted wave goes out. So here's one that's above the critical angle. This is a real glancing angle here. And the only thing that can happen for all the light that hits this boundary is it's all 100% reflected. Total internal reflection. No light gets out. Wow. We've trapped the light. We've trapped the light inside this high index of refraction medium. What does it take to do that? Well, what it takes is two things. First, you'd like to have a high index medium that you want to trap the light in. The higher the better, the higher you can manufacture. And then we need the light to try to only escape at a very glancing angle, so it'll be totally internally reflected. Let's look at the mathematics. Actually, the arithmetic's very simple. We take Snell's law here, divide both sides by n1, and of course, by definition, in this diagram here, theta 1 is the angle of incidence, and so theta 1, sine theta 1 here is going to equal n2 over n1. Let's suppose n2 over n1 was fairly large. We could make this like 1.3, 1.5 or something. Then you multiply that times sine theta 2. This is the angle coming out, and this has to be, of course, less than 1. You can't have sine theta ever being greater than 1. So, how big could sine theta 1 be, and we can still satisfy this condition? Well, the critical angle is going to be when this is exactly equal to 1, because you can't get any higher than that. When is this exactly equal to 1? Sorry, when is this exactly equal to 1, and therefore when is this exactly equal to 1? That is solved. We just have to take the arc sine of both sides, and the condition for that, so the condition here is that sine theta c is n2 over n1, or the theta critical is the arc sine, the inverse sine of n2 over n1. So if n2 and n1 are equal, there's no problem at all. It's trivial. There's no refraction. But if n2 is a lot larger than n1, then theta critical is going to be it might be a lot less than 90 degrees. Let's look at some specific cases now. Here we have water, for example. So water has an index of 1.3, 1.33. That's the higher index medium. And then let's say it goes to air up here, which is a lower index medium. This is the same drawing I showed you last time. There's the theta critical angle. And if you come in at a larger angle away from the normal than that, you merely have total internal reflection. There's the condition. Sine theta cannot ever be larger than 1. The most extreme case you can have is sine theta equals 1 for the outgoing refracted wave. And here's an illustration of this in water. Here's a goldfish bowl. We took out the goldfish to not harm their eyesight. And we have two laser beams coming in, slightly different angles. They go through the air, then they pass almost straight through, because they're almost 90 degrees normal, into the water here where you can see them glowing a little bit. And then there's a flat mirror here which reflects them at slightly different angles. Angle of incidence equals angle of outcidence for both rays. One of them then hits back to the water at a fairly steep angle, fairly far away from the normal, and it just manages to refract. It gets out. So that light ray did get out. However, this steep, even more grazing angle of incidence of this lower light ray here, it's totally internally reflected. None goes out. See, none is going out of the water. So that lower ray that came in at above the critical angle off the normal, it's totally internally reflected. By the way, there's another example, if you look closely at this one, of more total internal reflection happening at a large grazing angle. What happens? This ray, some of it bends back out when it hits the air here. It's refracted, but some of it bounces off the curved side of the glass here, bounces up at a very steep angle, and notice what happens here. It doesn't escape. It is also internally reflected here. So that's two examples in this diagram of total internal reflection between an air and a water medium. All right, let's look at the formula then for air and water. This is a classic case. As I said, the solution for the critical angle was that the critical angle is the arc sine, that's the inverse sine of the low index over the high index. And so, of course, sine then, in other words, what angle has a sine of that angle, which is 1 divided by 1.33. Well, of course, sine can take on this value. Looks like it's fairly close to 0.7. I was just guessing like 45 degrees. Okay, this is actually a little bit bigger than 0.7. The actual answer, if you plug it into a calculator, making sure that you're keeping track of the units here, that your answer comes out in degrees, is the critical angle for an air-water boundary for total internal reflection is exactly 49 degrees. You can take that to the bank. You can take that to the beach. Always true. And this leads to some interesting consequences, which if you've ever been, it kind of helps to dive to notice this effect. It's particularly noticeable like if you're a fish, for example. So here's a diver, and a diver is experiencing total internal reflection when you look out at objects that are standing outside of the water. Some people might want to look at this palm tree. This diver is looking at the lady over here. And you'll notice that if you look straight up, there's no problem. You can see this cloud, for example. You can see that cloud, no problem. The light from the cloud comes in here and bends. It gets to your eye. So there's your view, the diver's eye view. You can see the clouds because they're less than 49 degrees away from the normal. So the light rays there will come down and bend no problem. However, notice what happens to light rays which for you to look at them are 49 degrees away from the normal. So suppose you're down here underwater. You look at 49 degrees away from the normal, that's the critical angle for the water-air interface, for total internal reflection. So the light rays actually skim the surface of the water here. So in principle, you can't really quite see the lady's toes in this diagram, just barely. You can see her ankles and her lovely legs and so on, but not her toes here. What happens if you try to look down here to something that's lower, like below her toes? Maybe she's stepping on a crab or something. You can't see it. You can't see it because you'd be looking at larger than 49 degrees, and so the light rays that you'd be looking at would have been totally internally reflected. Notice that these arrows go both ways. Right? On the previous diagrams, we had light rays emanating from the eye of the diver going up and over, and I said that was total internal reflection. When the light ray hit at a really glancing angle, it was reflected back. Well, of course, by the symmetry of light, exactly the same thing has to happen. These paths are the same if you go from left to right. Right to left, left to right, it's the same path. And so what you actually see if you're underneath the water, and you probably notice this if you've looked up when you're diving and you try to keep water from getting in your nose, and it's rather uncomfortable, but if you are careful, then you see a kind of a small world outside your water tank, because the diameter of this field of view is, aside from little shimmerings in the water and so on, the diameter, this really should be a circle if the water was calm, the diameter is exactly the radius is exactly 49 degrees here. So you can see from the zenith, of course, out to 49 degrees that way, 49 degrees that way, 49 degrees that way, and you cannot see anything. If you look at larger angles, all you're going to see is reflection of the underwater surface here. You'll be looking back at the dirt or the gravel that's under the water. So that is total internal reflection that is experienced by a fish. It's very, very useful now if you want to redirect light, possibly over very large distances. You can make a light pipe. So this is a very useful application. Fiber optics is all about making light pipes. And the idea of a light pipe is you take a transparent medium that can transmit some kind of waves. Maybe infrared waves work very well here. This could be made of some kind of silicon material, and you can get it to have a very high index of refraction inside. It's air outside. And so as long as the light rays, these might be laser beams, are only reflected when they're trying to escape the light pipe here, but as long as they hit the light pipe at a very large grazing angle alpha, which happens to be larger than the critical angle for this material at this boundary, it'll be totally internally reflected, and then if you don't twist this thing too hard, it'll be totally internally reflected on the other side when it bounces over here, and it'll totally internally reflected here. It'll keep bouncing back and forth, bum, 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 totally internally reflected, in some case, for miles. The light could go for miles. And if you gradually curve these tubes around, don't make any of these bending angles too steep, too sharp, then you can turn light to whichever direction you want, maybe flexibly if this stuff is material. So here's some roses, and the RO light has come here, and it's been bent gradually here, so you can read it at 90 degrees away. It's literally a light pipe. That's what fiber optics is. It's a great breakthrough of the 20th century. One last thing I need you to know about is all of Snell's law that I've been telling you. In fact, the whole phenomenon of refraction, I've been assuming the index of refraction n. But you'll notice in some of the slides, I specified what the wavelength of the light was that we're talking about that's refracting, because not all wavelengths of light reflect the same. And the reason for that is almost any kind of transparent medium you can think of, whatever dielectric material it is, the index of refraction invariably increases a bit as the wavelength decreases. So bluer light, when it passes through glass, for example, quartz glass, various kind of glasses, as that light, if you make a shorter and shorter wavelength, go from 500, 450, 400 nanometers, which is blue light, you find that the index of refraction of the medium effectively becomes larger. What that means is that the angles of refraction given by Snell's law will be larger at shorter wavelengths. To put it simply, the shorter the wavelength of the light, the larger the refraction, the larger the angles that it bends away from the normal. So here's white light, which of course, even going back to Isaac Newton, we realize is a mixture of various colors of light. The red light has the longest wavelength you can see, 700 nanometers. It bends a little bit here, but not very much, because the index of refraction in red light for this glass prism is not very large, and it's a little bit larger than 1. Yellow light, green light, and is larger. It bends more again at the second surface. The biggest bend that you'll see is for the shortest wavelength light, around 400, maybe 350 nanometers. That corresponds to a large index of refraction in glass. Bends a lot here, bends even more as it escapes back into the air. So what you have done is you started out, this is what's so useful about prisms, you're benefiting from this fact, the real life fact that the dispersion means that the refractive index n will get larger at smaller wavelength. And so just going back to Newton and other people, you send in a mixture of red, orange, yellow, green, blue, Roy G. Biv, whatever it's called, all these different wavelengths. They refract by different amounts, more as you go to shorter wavelengths. You've spread the light out. You've separated the different wavelengths, its constituent parts, into a spectrum. Hooray! Our first discovery of a spectrum, and it was very easy to make because of this real-life property of wavelength dispersion, of a increasing index of refraction in the material with shorter wavelength. Now, of course, that might be bad. Maybe you wanted to make a photograph, for example, with glass lenses here and prisms, and you didn't want the red to come to a different place than the blue. You didn't want there to be what's called a chromatic aberration in your photographs. So there might be some circumstances in which this dispersion property of most materials is a good thing. If you want to make a spectrum, it disperses the wavelengths. Or in some cases it might be a bad thing, and you might actually try to compensate it or look for another scheme for bending the light around. Depends on your situation, but that's life. And one of the prettiest applications, which of course is not man-made generally, is what happens when light waves, which of course a combination of Roy G. Biv, red, orange, green, yellow, and violet light, passes through a water droplet. Water droplets, when they're just up in the air, suspended there in a mist, it's a fog, or after a rain, the air has got all these water droplets, which are approximately round spheres. So let's look at what happens to one bundle of light rays that might be coming, maybe you're standing here, and a light ray is coming over your shoulder here. That could be from the sun. After the storm has passed and the clouds are beginning to back off, but the water is still full of, the air is full of these water droplets, white light comes in, and now you see that water also has this property. The red wavelengths, that's the long wavelengths of light, are refracted a little bit when they pass from the air into the water boundary here. The blue, shorter wavelength light is refracted more, so it goes down at a steeper angle here through the water. Then they get to the other surface of the water. This is from a high index to a low index. Some of it will pass on through, not shown in this diagram. Some of it will exit out of the water, going down there. But some of it will be reflected. Just like you have a mirror here, angle of incidence equals angle of outcidence. Since the red light reflected off a higher point, it's more curved up here, it's going to go down more. The blue light was reflected closer to vertical here, so it gets reflected up like that. So they were separated coming in. They bounce, they're still separated, and then they get even further separated when they exit the water because refraction happened here, reflection happened here, which did not make any difference really for the two light rays. It just preserved the separation they had. But more refraction happens down here a second time. The blue rays bend more away from the normal because the index of refraction of water is higher for violet rays. The red rays also refract some, but not as much as they exit. So the combined effect of these two refractions at this boundary and this boundary is that the violet rays come back down here at about 40 degrees from what they came in, whereas the red rays come in at 42 degrees. And if you look carefully, you'll see that the light is coming over your head here. The red rays are coming back at you at a fairly large angle. 2 degrees away are the blue rays there, and at about 1 degree, that's about 41 degrees yellow, is in between. In other words, it's a rainbow. A rainbow, of course, is the light you see from a combination of many round water droplets producing these refractions. So they bend the blue rays more and the red rays less, as you can see here. And, oh boy, there's a second rainbow there. That actually corresponds to double reflection in the water drops. Not going to make you know that for this course. It's the reverse of the other situation. The red is on the inside and the blue is on the outside. But again, it's just illustrating how refraction of light waves gets larger angles for shorter wavelengths. That's it for refraction. Everything you need to know to do well in this course, to do well in exams, to ace the MCAT. There'll be some problems on this, I guarantee you. This has many real-world practical applications. Now, I already started talking a few points in the last few slides about reflection, which in some ways looks like is going to be simpler here. So let's talk about reflection now. I could have started with that first. Reflection is nice because it does not depend on the wavelength of the light here. In fact, it's so simple because the angle in equals the angle out, the angle away from the normal. So in some ways, if you're comfortable with Snell's law and refraction, you ought to be even more comfortable with reflection. It's fairly simple, but there's some pretty interesting phenomenon that happen from reflection. So let's look at some of those now. In this course, I'm going to be only thinking about an ideal case. Right? Physics courses are often about ideal cases where we're reflecting off of a medium which is, let's say, a perfect conductor. Could be a thin layer of metal, like a thin layer of silver or aluminum that's coated onto a glass substrate. That's called a mirror. And the reason it works is that there are free electrons in this conductor which will move around and respond because this is an electromagnetic wave. Say the electric field is oscillating this way, back and forth, back and forth. It's going to move these electrons back and forth when it impinges on their space in the conductor. So they'll vibrate back and forth in sympathy, and then they will launch a reflected electromagnetic wave back out in the opposite direction it came from. And my idealization here is that this surface is going to be perfectly smooth. So I'm always interested here in perfectly polished, perfectly flat. I mean, this is even flat down to the scale of a wavelength of light, which you can do quite easily, get a good cloth or good optical quality stuff. This is a good optical quality surface. In real life, of course, you might have sheets of metal and so on that are rough, and if you look at it at a microscopic level, the surfaces are bumping up and down. That'll reflect light, but it won't really be able to reflect light sharply following exactly this perfect geometrical reflection law. So you won't, for example, get nice images to form. You'll just get a general glow of light reflecting off of this rough medium. So I'm not interested in this case. I'm interested in cases where people have maybe gone to some special effort to actually make a very flat, smooth surface, or I don't know, maybe it's a very calm pond, on a lake or something, where this reflection obeys the ideal law of reflection. What is the ideal law of reflection? I think I've got it in the next formula here. The law of reflection is so simple, you might even not have realized this is a law. It's kind of obvious by the symmetry of the problem. The angle of incidence, always, just as we've defined before for Snell, the angle of incidence is how far your light ray is away from the normal. Don't get confused. It's not this angle to the surface, it's to the mirror. It's the angle from the normal to the mirror. The normal to the mirror is always perpendicular. It's a ray that's it's a dotted line here that's perpendicular to the surface of the mirror at the point where the light ray hits the mirror. You got to draw your normal here and then measure the angle like that. And the angle of incidence, as I always remember it, is for reflection is exactly equal to the angle of outcidence, or the angle of reflection, as they call it here. Not refraction, but reflection. How simple is that? I can hardly imagine it could be anything else. Here's a side view of it. So this angle is the same as this angle. Gosh, that looks so simple. But if we use that, it's actually going to turn out to be very powerful. Let's start solving some problems here. Now, notice that I took a very simple flat surface here. So the normals are always straight up because my flat surface is always horizontal here. It's like in the x direction. This is in the y direction. But if I had a curved surface here, this could be like a curved mirror. I could curve it upward. I could curve it downward, convex mirror, concave mirror. Then the normal would have to be defined carefully. It's the vertical or 90-degree vector at the point of the mirror where the light hits. And it could be different if it's a curved surface. I'm just starting you off easy here with a flat surface where the normal is always straight up. But when we get more complicated, the normal will be in different directions, different locations on the mirror. So let's see what wonderful things mirrors do. You sort of know this is the whole point of a mirror. A mirror reflects light from another object back at you that you wouldn't have seen if the mirror weren't there. And remember about your eye? Your eye just traces back the light that comes into it, assuming it was always traveling forever on a straight line until it goes back to the source of the photons. So this is basically what happens in a nutshell. We have light from a point P. It's a source of light rays. Now, of course, you could just look down and see P, because P is sending some light rays up to you. No, I want to look over here. I look over here towards the mirror, and lo and behold, if I look at the right spot, if I look at spot B here, I can see light rays that actually originated from P. They originate down here below me. They came up, hit the mirror, bounced off. This theta angle of incidence has got to be exactly equal to this angle theta of reflection. So the incidence is the outcidence. And so those light rays enable me, they traveled from P to my eye. But where does my eye think that they came from? Right? Your brain processes it and assumes that the light rays came from behind the mirror. That's impossible. This is a solid surface here. Light actually doesn't travel through mirrors generally, so you can't see what's on the other side of a mirror, but it looks like you are seeing it. It looks like light actually originated from a point over here. This pink point P is an image of the real light source P, and the light rays didn't actually travel on this dotted path here, but it looks like they did, because the light rays, you see one light ray coming up like this light ray that went from the object P hitting the mirror straight on comes straight back out. So it looks like light rays are actually diverging from an image behind the mirror. They didn't actually travel that path, so the image is called a virtual image. Not a real image, because the light rays didn't actually travel from this point. They just look, by the time they get to your eye, like they did emanate from that point. And now you'll notice a great symmetry in the problem. This triangle here is the same as this triangle over here. Why is it the same? Oh boy, 10th grade is coming back to me. Oh, all those socially awkward moments and so on. When I was trying to do geometry and everybody else wanted to do fun stuff. Well, I seem to remember that if a triangle has two angles the same, actually all the angles the same. This is a 90-degree angle. This is theta. This angle here is also theta, because incidence equals outcidence. So that theta is the same as this theta. And one leg of the triangle, the height of the triangle is identical, h. So these are identical triangles. I guess the word is congruent. God, I thought I'd forgotten that one. So this triangle is just a flip of this triangle. So in particular, here's the money question. How far behind the mirror is the virtual image that's formed of P? Well, if P is a distance S in front of the mirror, this virtual triangle has to be identical, except it's just flipped here. So pink P, the virtual image, has to be a distance S prime, but it's going to be the same as S. In this particular case, because it's a flat mirror, S and S prime have to be, in this case, identical. So the image looks, so just take a simple case. Suppose you're 1 meter in front of a mirror. Suppose this is 1 meter, suppose this object is 1 meter in front of a mirror. It will form an image 1 meter behind the mirror. All right, now, let's get a little more complicated here. What do people, this is LA, I mean, people are very into themselves, right, and their appearance. So this actually might be you standing in front, not you, but, one of those self-obsessed people standing in front of a mirror, and P might be, for example, your waistband or something like that. And so you want to see how this belt looks on you. Okay, we didn't fill in this whole diagram here. So what you're actually looking at is part of your own body here. And so what you'll see, of course, is an image of you standing over here. And what this diagram shows is, if you stand 1 meter in front of a mirror, you will see an image, a virtual image of yourself. You can see your head. If you look up here, you can see your head. If you look down here, you can see your belt. If you look further down, you might be able to see your shoes here. You'll see an image, here's the money, as if you were standing 1 meter behind the mirror. You see an image of what you would look like at a distance of 2 meters, because you're 1 meter away from the mirror and then 1 more meter away from the image. So if you stand 1 meter away from a mirror, you see what other people see when they stand 2 meters away from you. That's the whole deal, if you understood that. Now we can do some interesting problems. Now you notice the tricks in this case were to locate the virtual image. What we did is we took some rays starting from the object. I took one ray that went straight to the mirror, comes back at you. I took one ray that went up here and comes back to your eye, and I traced the rays backwards, and the rays, these two rays, intersected at a virtual point of an image, which is this pink P. That's where they intersect. That tells you where the image is. And then we noticed, we compared this triangle to this triangle, and we look for triangles that are similar or identical. And so this is another way of looking at it. Now I'm going to actually solve a useful problem. If you're running a department store, then, or heck, a bathroom or whatever you're in charge of, hopefully, because you've learned physics, you'll be able to be in charge of even more sophisticated operations than a bathroom. But anyway, this might be your entry-level job. I'm going to take care of the mirrors in this bathroom, and or let's say it's a summer job at Macy's or something like that. And people, your department sells all kind of clothes, headwear, footwear, and everything. And apparently the people are coming in to your dressing rooms and they want to see their entire body. They want to see everything from up what they're wearing on their head down to their feet. Now, in this case, I'm going to oversimplify things a little bit here and assume that your eyes are actually exactly on the top of your head. Is not exactly true. But anyway, if you had eyes exactly on the top of your head, here's my question. In your store, how tall a mirror is required so that you could see all of yourself? You might be thinking, what information is missing from this problem? It didn't say how close I could stand to the mirror. There's a mirror, say there's a mirror like this. I could get really close to it, or I could stand far away from it. That's right. The problem doesn't say that. Because of these triangles, it doesn't matter whether you stand close or far away. You'll only be able to see a certain fraction of yourself if the mirror isn't big enough. So if you have a little small mirror, you'll be able to see your face, but you won't be able to see your belt. You certainly won't be able to see your legs. You're saying, well, I could see my legs. Yeah, I could take this little small mirror, and I could move it down here, and then I could get a view of my belt or even my feet here. But then I couldn't see my head. You see how a little mirror, I have to move it up and down. In other words, what I really need is a bigger mirror. It's a series of these mirrors. Some part of it obviously needs to be straight across so I can see the top of my head, and then some part of it is going to have to be down here so I can see my feet, and then all of that mirror has to be filled in so I can see what shirt I'm wearing and what pants and so on. I mean, assuming I'm wearing clothes here. We keep a respectable shopping mall here. What's the minimum size mirror that you need, the minimum height mirror, so that you could see everything from head to toe? Let's look at this. Here now is an idealized person. I hope your shoppers don't look like this. But there's their feet, and their eyes are at the top of their head. So here's the actual object. So light rays emanate from the object. Let's just look at the head, the top of the object here. And let's follow the two light rays that we did in the previous diagram. Some light rays emanate from your head and go straight across. Horizontally, they hit the mirror. Looks like we're probably going to need some mirror up here. And then since they're exactly normal, they come straight back at you by symmetry, and you see them over here. Duh. So I'd like to have some mirror up here. I need some glass reflecting here to see the top of my head. How about this light ray here that's emanating from my head, going down to the base of the mirror at the floor? It goes down there and then reflects down here, actually be into the floor, unless there's a transparent floor here. All right, so this light ray appears to have emanated from where? Let's trace it back. Light rays these are dotted lines, not actually traveling this path. But the light ray looks as if it traveled from here, because that's the point. If the light ray originated from here, an image of your head, this is the top of your head over here. If the light ray originated from here, it would send one light ray in this direction, which you see, and it would send one light ray down here. So this is just confirming what we said in the previous slide. There's an image of you, and the image, because this triangle, see this triangle, is identical to this triangle here. Not only is the image an equal distance behind the mirror, as you were standing in front of the mirror, but also, what about the height? The height of this image, y prime, it's identical to your height. It's the same as y. This triangle, same as this triangle. So the image, if you're 1 meter in front of the mirror, the image is 1 meter behind the mirror. If you're, 1.5 meters tall, then the image of you is also exactly 1.5 meters tall. Special case of a flat mirror. It's sort of a trivial case. In other words, what's the magnification here? Well, so you're 1.5 meters tall, that's y. Your image formed by the mirror is also 1.5 meters, so the magnification is y prime over y. It's trivial. It's just 1. Height of the image, same as the height of the object. So a flat mirror does not magnify you or demagnify you, which I guess is fine if you want to see, do these clothes make me look tall? No, they don't. Not in this mirror. It makes you look the height that you normally are. Now, here's the money question. I want to be able to, I'm looking at my image here. That's me standing, say, 2 meters away. That's S plus S prime. I want to be able to see light that looks like it's coming from my feet here. There's an image of my feet. Where do I have to look? I have to look along the red line here. The red line goes through here. In other words, although I'm standing 1 meter away from the mirror, I'm actually 2 meters away from the image. So I actually only have to look halfway down to see my feet. Let's generalize with the answer then. Whatever your height is here, see this is your height here, compare that to this triangle here. This height, as you can see from the symmetry of the problem, this height here, which is the required height of a full body mirror, is what fraction of y prime? Half. This mirror has to be half of your height. If it's half of your height, it's like a little window. So window here, allowing you to see your entire image from head to toe back here. So if you're 6 feet tall, you will never, ever, wherever you put the mirror, wherever you stand, you can stand right next to it, you can stand 20 feet behind it. Your mirror has to be at least 3 feet tall, or you will not be able to capture all simultaneously everything from the top of your head to your toes. All right, there's a great deal of symmetry in this particular problem, and so we just use some geometry here to solve that deep mystery. Go and next time you're in Macy's and ask them how tall. So the mirror doesn't have to go down to the floor. Hooray! The manager's going to be happy here, right? You don't need a 6 foot tall mirror to see your entire reflection of your 6 foot tall body. You only need a 3 foot tall mirror. We have saved Macy's millions of dollars here, but can get these shorter mirrors. Good for you. Now you're moving up. Now you can be like a junior executive in charge of acquisition of mirrors here. Save the company millions of dollars. So here is the full description of what I was going through with mirrors before. And this applies even to mirrors that are not curved, although some of the results that are not straight. Curved mirrors will produce these things too, but some of the angles and the sizes are going to be different. And so on. This is a very simple case. So as I showed you before, okay, it's a flower now, I don't know why. It sends out some rays from the bottom. Some rays go up a little higher, some rays go down. So then they reflect off, incidence equals outcidence. So these higher rays go up here, these lower rays go up here. Then from the top of the flower, some rays go low, some rays go a little higher. They reflect off at slightly different angles. And notice what's happened. The rays that originate up here at the top of the flower diverge. And then they reflect, and they're still diverging, but now your eye sees two diverging rays, and your eye wants to trace them back to the point where they converge. And as we saw in the previous diagram, they converge at a point P prime, which is the virtual image. And if you look at the symmetry of this diagram, the distance D, it was called S, sorry, now it's called DO. The object distance, the distance between the object and the mirror, in the case of a flat mirror, is exactly equal to the image distance. The distance from your virtual image, P prime, to the mirror. So DO in this case is equal to DI, the image distance, and the height here of P, that's the actual real height of the object, is also exactly equal to the image height. The magnification is 1 here. And the image is virtual because the light actually is not coming to your eye from P prime. And another thing to notice, of course, that isn't guaranteed with other kind of mirrors, in this flat case mirror, the orientation of the base, there's the bottom of the, let's look over here, there's the bottom of the image, comes up to you from down there. The top of the image comes up to you from up here. In other words, this image is not inverted. It's upright, or erect, as the old-fashioned textbooks call it. It's an upright image produced by this mirror. So that's pretty much all you need to tell me about this image. Where it is, what its orientation is, and if it's magnified or demagnified or has a magnification of 1, as in the case of a flat mirror. So now we've defined a lot of very useful things that we're going to need for all image formation of all mirrors. We're also going to use it for lenses too. In other words, we're going to use it for the next few weeks here. It's fundamental to optics. We've got DO, which is the object distance from the mirror to the object. We have DI, the image distance. Now, the way there are different textbooks, I'm sorry to say, define the sign of DO and DI in different ways, but as long as you stick with one sign convention and don't waver, don't ever change from that, you'll be okay. So I'll show you what our sign convention is in a minute. Now, there's one thing I didn't tell you about. We realized that a flat mirror makes an upright image. It's the same magnification of 1. It's the same size as the original image. There's one thing I didn't talk about, which is more complicated. What is the handedness of the image? Well, let's look at this. Suppose, for example, that I put my, what is this? I'm going to put my left hand in front of a mirror here. This is someone's left hand here, obviously. And we try to draw all three of the spatial directions here with our left hand. I've got every one of my first three fingers is 90 degrees away from the other finger here. That's so we got a left-handed system here. I'll point the thumb in towards the mirror. The middle finger is going out that way, and the index finger, I'm not trying to do anything nasty here, is pointed straight up. What is the image of my hand? So now I'm looking in 3 dimensions at the image. This is a little more complicated than what I did before. Well, the middle finger, of course, we see an image going in the same direction, right? It's an erect or upright image. So since my finger was going off to this side of my real finger, the image of my middle finger is going that way also. And of course, this is obvious. This is just from the same previous diagram. The index finger is going up, so obviously the image of my index finger is also going up. No surprise there. These two fingers have to be like that. But notice what's different here. I see the thumb pointing back at me because the waves had to be reflected and reversed. So my real thumb is pointing towards the mirror. But my virtual thumb, the image of my thumb, is pointing back at me, and you can see that's no longer a left hand, guys. That is a right hand. See that? So a left hand produced an image, and the image looks like a right hand. The image has been reversed. The handedness of the image has been reversed by the mirror. Here's an example of this in case you forgot. There's the real hand of the person. It's on top of the mirror. This is a nice clean mirror. Makes a really good image. There's the image of the hand underneath the mirror. And although it was a right hand, that looks like a left hand. The person has not put their left hand here. There's no left hand anywhere in here. This person could, be an amputee. Doesn't even have a left hand, but the mirror makes an image that looks left-handed, and you can see these letters are backwards. It's some diabolical message. Oh, it just says hand there. All right. Secret code. I'm writing reversed. Anyway, so that's what mirrors do. The image, of course, both images are erect. They're not inverted, but the handedness is reversed. Here's a fun question when you combine two mirrors. You might have been thinking about that last. Let me make a comment here. Mirrors are wonderful. You get to see a virtual image of yourself that's the same size as you are, and it has a lot of similarities, but it has a different handedness. So there's a limitation of mirrors. As I said, most of these mirrors people are using to look at themselves. You do not see yourself in a mirror the way other people see you. Isn't that deep? It's philosophical. A mirror does not allow you to see yourself as others see you. You see a different handedness. In other words, your face is inverted. Not inverted, it's reversed from what other people see. And most people's faces are not perfectly symmetric and so on. And so if you sometimes you look at yourself in a mirror and then you look, for example, at a photograph that someone took at you, they look to some extent like different people. It's not really the same. If you really want to do this right, suppose you're in the acting business in Hollywood and you want to be able, you're doing makeup and so on, you want to be able to see in real time. You can't take pictures all the time of yourself. There's not always a photographer around. You want to see in real time what you actually look like as viewed by the director, for example. A mirror that shows you as you actually appear to other people. Could you do that? You cannot do that with one mirror. Wonder if you could do that with two mirrors. This is a well-known trick in Hollywood. Put two mirrors, for example, at an angle with respect to each other, 90 degrees like that. Now, I'm going to have one object here. Now, this is a funny, different orientation from what we had before. It looks to me like you're kind of lying down here. This could be your belt buckle here. Your head is up this way. You're tilted over in a funny direction. But anyway, or maybe this is just another object that you want to look at. You're not just obsessed by looking at yourself. Anyway, what kind of image is going to form from an object here that's in front of two mirrors. Here are the two mirrors, the two blue lines that are 90 degree, that are joined at a 90-degree angle. Well, now there are different paths that the light could travel from P to reach your eye. Let's do a simple one that we already know. Light rays from P could go down to here, and then they reflect. Incidence equals outcidence. They reflect and come to your eye, your detector. Light rays here diverge out a little bit more, go down to here, and miss your eye. Now, both of these light rays, of course, appear to be emanating. They appear to have originated at a virtual image of this orange dot. There's a virtual image. In the previous diagram, it would have been pink. P prime. We've already done that. That's fine. That's what we already did in the previous slides. No big deal. This mirror makes an image of P over here, which is P prime. Duh. What about this mirror down here? Well, of course, the same thing is. This P, this object, also can produce images off of this mirror. So, for example, the light could go down to here, bounce back to your eye traces it back to a virtual image P double prime. So this mirror here, this is what we already know. This mirror here was responsible for making an image P double prime of that. This is the actual object. That's the only thing that's actually real here, plus you. You're real, the mirrors are real. This is a virtual image made by this mirror. Here P prime is an image, virtual image, made by this mirror. But now here's the fun part, and here's why we stuck two mirrors together. Remember that scene in Deer Hunter where to save their lives they're playing Russian roulette, and it's dangerous enough with one bullet, and is it Robert De Niro character? He says, 2 bullets. I've got to have 2 bullets here. You can have 2 reflections and the light could still get to your eye. We're going to team these mirrors up together. How would that work? For example, well, it's actually not shown here, but the light, oh, here it is. Here's one. The light could emanate from this object. It could go down here and bounce off this mirror first. Now, bummer, it's not going to your eye. It missed your eye. Wait a minute, there's now another mirror here. It bounces off that mirror and comes to your eye. It's a bank shot. Ever do that in pool? Bounce, bounce, 2 reflections gets to your eye. That's what this new setup gives us. The chance for a double reflection. Boom, boom, boom. And your eye thinks that there's a 3rd image down here. It's a double reflection, P triple prime. So your eye will see an image. Suppose this was a light bulb. Your eye will see one light bulb apparently up here. Your eye will see another light bulb down here. And maybe it's a little dimmer if these mirrors are a little bit dirty. But they'll be, because it's a double reflection, your eye will also see an image of a light bulb down here. It looks sort of in the corner of these 2 mirrors. So there's a 3rd image down here produced only by double reflections because we had 2 mirrors. That's going further than what we had in the previous slide. Now, this first reflection reversed the handedness. So if this was like a right-handed light bulb, suppose it had a right hand drawn on it, when it bounces off here, it's left-handed. Then it bounces again, and left gets reversed again to right-handed. So these images are reversed. The handedness is wrong. It's not the same handedness as the actual object. What about the double reflection? You got it. It has the original true-handedness of the object that produced it because it was reflected twice. It was reversed and then reversed again. So if you look at, suppose this is you, this is your face. You're really interested in your face here. And if you look at your face and you look at the doubly reflected image of your face, so you look into the corner of the mirror there, it's a little further away. It'll be like it looks a bit smaller image of you. But anyway, you'll see an image of you that has the same handedness. It's not reversed from what other people see when they look at you. You will see yourself as other people see you, and you will attain great spiritual enlightenment, even in Hollywood. Wonderful. And I'm going to skip that. Now, if you want to get really fancy here, this is the fanciest I've seen with mirrors. Why stop at a double reflection? You could put 3 reflectors together, making half of a cube here. So I've got one reflector that goes up this way, one that's flat down here, and one that's flat down here. These are halves of a cube. They took a bunch of these reflectors, and the astronauts left them on the surface of the moon. There's the boot prints around there of, I forget if this is Armstrong or one of the later ones, maybe Harrison Schmitt. They left these reflectors here. And what is the use of a triple reflection in a cube? The beauty of this is, if a light ray comes in from any direction, it bounces once off of this surface, incidence, outcidence, then it bounces to this surface, then it does a triple bounce off here. After it has bounced off of these 3 surfaces, assuming that they are exactly the 3 faces of a cube, assuming that they're exactly 90 degrees with respect to each other, that mathematically guarantees that the triply reflected rays will be coming back in exactly the same direction as the light rays came in. And that's true if you shoot a laser beam at these cubes from any direction. I could shoot the laser beam down here, they'll reflect it back. I could shoot it down here, they'll come back. Cool. It's almost like a mirror that follows you around, isn't it? So clever. That was absolutely essential because the astronauts knew that Lick Observatory and the 3-meter telescope that I use outside of San Jose, California on Mount Hamilton was going to be equipped with the first super powerful laser in the early 70s, and they were going to be shining lasers. They didn't know which direction it would be coming. It might be coming from here. Depends on where the moon is. It depends on where the Earth is. Laser might be bouncing this way, but whichever way the laser beam came from to this lunar reflector, because it was designed with these cubes, these half cubes, it would definitely send all of the laser light back towards the emitter. It would towards the transmitter of the laser waves. It would send it right back to the observatory that launched from the same telescope that launched the laser, so that we could spot the reflection. I talked to the guy who actually did this experiment in the 70s. Of course, I wasn't at Lick Observatory then. I was a kid, but it was very exciting because this actual cube, half-cube reflector here is how we know precisely, I mean precisely, how far away the moon is from us. It's how we've measured, of course, that the moon is getting a little bit further away from us every year or every century. Actually, it takes a long time, and that's due to torques on its orbit from the Earth. That's a complicated 6A problem. But anyway, that's a rather fancy application. Now here's an interesting question. Suppose you were to rig up one of these 3-corner half-cube mirrors. This is getting a little fancy. You won't find this in a Hollywood dressing room, but that way you could look at yourself from any angle and you would see yourself in this. Would you see yourself as others see you? Or would the handedness be reversed? Well, let's see. It's a triple reflection. I'm sorry. So you'll be reversed again, the same as when you look in a normal mirror. You'll not be seeing yourself as others see you because there were 3 reflections. One reflection goes right-handed to left-handed, second reflection makes it back from left to right, and the third reflection messes it up again from right to left. So if you send in a right-handed image, after 3 reflections, it'll come back left-handed. But otherwise, at least it will come back in the same direction that it was launched. So very useful stuff. That's enough for flat mirrors. I'm done with flat mirrors. Now we're going to go on to curved mirrors, which are frankly more interesting and even more useful.